Alright, good morning everybody. I want to talk about just some basics of the exponential functions that we're coming into. Alright, so far we had y equals mx plus b. This is my linear function. Then we came across the absolute value function, which is y equals, and we talked about an a value, x minus h plus k. This was my absolute value function. Okay, and now we're going to talk about our exponential function. And we're going to talk about this in the form of y equals a times b to the x power. Now there is also a minus h and a plus k here, but for our purposes this year, we're just going to look at the a times b to the x power. Alright, so what we got here? So a couple things you need. So this is going to be my this is going to be my I'll put this in text here. This is going to be my y-intercept. Y-intercept on the graph. There's an R there. Okay. This one here. This one is I'm going to call it two different things here. Okay. This is also going to refer to this as my base. Okay. And this is also going to be my exponential. This is going to be called my growth factor. Growth. Okay, and I can refer to it either way, or rather than growth factor, it can also be known as my decay factor. And we'll talk about that in a minute. Okay, so for graphing purposes, we have so the function is y equals a times b to the x power. Right, this is my exponential function. Okay, so this is my exponential function here. Let's blow that up a little bit. Beautiful. And voila. Okay, this is my linear function. This is my absolute value function. And now we have my exponential function. All right, I'm going to talk about how to graph all this in a couple of minutes. A couple of things I want you guys to think about is what are exponents? Okay, so exponents, if you have 2 to the third power, what does that mean? Does that mean 2 times 3? The answer is nope. That means I have 2 times 2 times 2. How many times? 3 times. That's my exponent. So if you have 5 to the fifth power, then that does not mean 5 times 5. That means 5 times 5 times 5 times 5 and times 5. A total of 5 times. And you can do the math on that and get your answers. And what you'll notice as you do 2 times 2, you get 4, 4 times 2, you get 8, and if you do it again, you get 16, and so on. And as you keep multiplying by 2, your numbers get very big very quickly, hence the term exponentially or exponential function. Alright, so basics. We have a graph, voila. All these exponential functions will have some kind of y-intercept. Now I'm going to look at a very easy one. I'm going to look at f of x equals 1 as my a value times, I'm going to do 2 to the x power. Make myself a little table here. What does this look like? Okay, so again, 1, like we said, was the y-intercept. Perfect. Okay, y-intercept of 1. Beautiful. All right, now, so when x is 0, y is 1. Well, let's hold on. So f of 0 equals 1. How? All right, let's take a look at another screen. So we have f of x equals 1 times 2 to the x power, and I just made my table. And wait a second, so if I do f of 0, that means I'm plugging in 0 in for my exponent. Okay, so one big thing that I look at right now is this piece here. So 2 to the 0 power. So when we do PEMDAS, parentheses, exponents. Okay, so this part would go first. So what is 2 to the 0 power? So on a separate screen, so 2 to the 0 power, and you can look up the mathematical proof for all this if you wanted to, but 2 to the 0 power is 1. 3 to the 0 power is 1. 4 to the 0 power is 1. Anything x to the 0 power is 1. Any number to the 0 power is always going to be 1. Alright, so we're going to embed that into our brains as 2 to the 0 power. Anything raised to a 0 power or 0 exponent is always going to be 1. Okay, so come back to this one. So that means I have 1 times, now what is 2 to the 0 power? And we just said 2 to the 0 power is 1, and 1 times 1 is 1, which is why when x is 0, y is 1. If you want to look at another example, f of 1 means, okay, so 1 times 2, and now this time instead of 0, I'm going to put in 1 for my exponent. Right, so here's my 0, 0 went in for x. Here's my 1, 1 goes in for x. Okay, so exponents first. So 2 to the first power is just 2, and 1 times 2 is 2. So when x is 1, y is 2. Okay, so let's take a look at a few more examples and see how that goes. We'll slide these over. Parentheses exponents, okay, PEMDAS. Alright, let me get rid of this. Alright, so now let's look at a couple more examples. Let's split that, okay. And how about f of 2? We did f of 0. We did f of 1. So we did f of 0, we did f of 1, let's do f of 2. F of 2 means, okay, so I'm taking my function 1 times 2 to the second power. Alright, my bad if you heard that noise, that was the dishwasher. Alright, so f of 2 is equal to, again, I'm going to do my exponents first. 2 squared means 2. So 2 squared means 2 times 2, which is 4. And 4 times 1 is 4. So f of 2 is 4. So my x values, I'm continuously adding 1 to my x values. Now I'll do another one. We'll do f of 3 for fun. Why not? F of 3 equals 1 times 2 to the third power. Now please recognize that what's changing, right? I'm always changing the exponent here, okay? And I'm always plugging in for the exponent, okay? So f of 3 equals 2 to the third power. 2 to the third power is not 6. What is 2 to the third power? 2, what does it mean? 2 to the third power means, we have a screen here somewhere. 2 to the third power means 2 times 2 times 2, which is 6. And 6 times 1 is, just joking, 2 times 2 times 2 is not 6. 2 times 2 is 4. 4 times 2 is 8. And 8 times 1 is 8. All right, so avoid making that mistake. If you want to write this out for yourself, that's not a bad idea. All right, 2 times 2 is 4. 4 times 2 is 8. 8 times 1 is 8. And here's this. And why not one more? F of 4 equals 1 times 2 to the fourth power, right? The 4 goes in for the exponent, which means 2 times 2, 4 times 2, 8 times 2, 16. 16 times 1 is 16. Amazing. So my x values are increasing by 1. Let me clean that up, make that look a little nicer. My x values are increasing by 1, right? Plus 1 each time. And my y values are being multiplied by 2 each time, which is where this growth factor comes into play, right? So this is times 2, and times 2, and times 2. Now, this is my y-intercept, which is attached to the a value, right? I said the a value is the y-intercept, and the base here, the growth factor, is what the y values are constantly changing by, or the y values, or my outputs, right? Those are the output, this is the input, right? So input changes by 1, you're increased by 1, the output changes by times 2. Increase by 1 times 2. Increase by 1 times 2. Right? And that's the difference between a linear and an exponential function, right? Linear will be adding 2 each time, in this case, if the slope was 2. And the exponential function will be multiplying by 2 each time because my base is 2. Now, on a side note, if this was f of x equals 1 times 3 to the x power, okay, and this is x and y, so when x is 0, y is 1. Okay, so this would be f of 0 equals 1 times 3 to the 0 power. 3 to the 0 power is 1. 1 times 1 is 1, so check. If we did f of 1, okay, f of 1 is 1 times 3 to the first. 3 to the first is 3. 3 times 1 is 3, so increase by 1. If x is 2, f of 2 is 1 times 3 squared, again changing my exponent. 3 squared is 9, 9 times 1 is 9. If I did 3 to the third equals 1 times 3 to the third power. This is 3 times 3, which is 9. 9 times 3, which is 27. 27 times 1 is 27. Okay, so now look, here's my base of 3, and how does that affect this? Well, times 3, times 3, times 3, right? So this base will be what I'm multiplying each output by as the inputs continuously increase by 1. Where am I starting from? Starting from a y-intercept. The y-intercept is coming from my a value there. Alright, so back to this one. Alright, so there's the whole table here. Now if I were to graph this, okay, I'm going to erase all this as we did that whole graph there. I don't think we need that, okay. So we said our function was f of x equals 1 times 2 to the x power. X is 0, we got 1. X is 1, we got 2, right? So this is coordinate 1, comma 2. X is 2, 1, 2, 3, 4. We got 4 here. So 2 comma 4. And now my graph is not that big. 5, 6, 7, 8. And there's that outgoing shooting up there when x is 3, y is 8. So that's very big. So this is going to shoot up very quickly. Alright, and now I'm going to steal something from a website. And let's pause. I'm going to pause for a second and drive us to that website. Switch screens to Desmos. So I'm going to write this in. Y equals, okay, so I got 1 times 2, right? And I'm going to raise this to the exponent. So if I hit Shift 6, it will give me a character there, and I'm going to put 2 to the x power. And voila. So here's my graph, right? So if we look at this individually, here's 0, 1. If I go to 1, I get 1 comma 2. Right? If I show this, I do 2 comma 4, and I can keep going. 3 comma 8. All right, if I zoom in a little bit, I can go to 4 comma, should be at 4 comma 16. And this, again, if we go back to our table here, are we good? So we got 0 comma 1, 1 comma 2, 2 comma 4, 3 comma 8, 4 comma 16, right? Just verifying here with our table. And you can run this up as long, I mean, you can zoom in and out of here, and you can see your graph just continuously getting bigger and bigger and bigger. I mean, this will shoot up very, very quickly. Where if this was a linear function, y equals 2x, and with a y-intercept of 1, right, so there's our same y-intercept of 1. Now, okay, when you shoot up, and if you look at the scale here, like I'm looking at my x scale, right, this is 0 to 5. So the linear equation is shooting up a little faster up until about this point here, and then that's when things start to change in the exponential function. At that point, after x is 2.66-ish or so, after that point there, then the exponential function really goes really quickly to infinity and beyond up here. I mean, it's growing a lot faster than your exponential, than your linear function, right? And on and on and on and on, okay? So that's the biggest difference between linear and exponential. All right, we have our graph there, and we can see it, and so on and so on and so on. All right, so again, just to recap, we have so far, we've talked about our function y equals a to the bx power. Again, in function notation, f of x equals a to the bx. A is going to represent our y-intercept. All right, for the honors class, we also talked about a being a reflection over the x-axis. All right, if you're in the honors class, you would know this when a is negative, or if a is greater than 1, then it's a vertical stretch. And if a is between 0 and 1, then we said it was a vertical shrink. All right, and again, we're going to exclude the h and k values, but h in this case, if there was a minus h and a plus k here, this would still be the horizontal shift right or left. This would be still the vertical shift up or down. All right, but we're not going to get that crazy. And then here, this b value is called the base, right? And the b value is the growth factor or the decay factor, and we'll talk about the growth versus decay in a couple of slides and a couple of other videos. All right, and the growth factor again is the what I'm multiplying by each time, what I'm multiplying the output by each time to get to the next output, assuming you're increasing by 1. All right, so the next piece before we stop this graph or stop this equation here, so we have all this, we have our table, and here's our graph. Now I started here, and then if we went back to Desmos, Desmos will show you, well, wait a second, this graph, I'm going to zoom in. it doesn't stop at the y-intercept. It does go on the negative sides, but if you look at how it goes on the negatives, what's going on over here? All right, so it looks like it's coming down, and does it equal? It looks like it's mirroring or touching the x-axis. Is it touching the x-axis? And the answer is actually no. All right, this is actually never going to touch the x-axis. So in order to tell our readers that this will never touch the x-axis, we're going to draw a little dotted line there at that x-axis. And I'm going to continue my graph here and say, okay, well, this graph is going to get so close to that x-axis here in the negatives, but it will never touch. And me drawing this line here will tell our readers that. So that line does have a name, and let's give this a name, and we'll give it something. And this is called a horizontal I challenge you to pronounce that. It's called a horizontal asymptote. Now, there's a horizontal asymptote at some equation. The equation is actually y equals 0. So if you remember from our past, just go to another screen here. If we just grab ourselves a graph here, my line, okay, if this is my x, this is my y, and I drew a random line here. Let's go with a nice thick red line. What is the equation of that graph? Well, this equation can have, let's say hypothetically, y equals 5. This was going through 5, right? And it's a horizontal line, so if I made it here, and let's say this y value is 3, then this would be the equation of y equals 3. So if I did it right here on the x-axis, then, well, here's 5, 4, 3, 2, 1, and then here is where y is actually 0. So if y is 0 here, then this equation is y equals 0. And that's what I have here. I have a horizontal asymptote at y equals 0. And I do it with that dotted line. And again, that's stating that this graph is going straight down. It's coming down from negative infinity. It's coming up. It's getting very, very close to the y-axis. And it's going, 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 going. And then as your x values increase, it's shooting up to infinity very, very quickly. But it is getting very, very close to 0. Does it touch 0? Negative. Now leaving me to my domain and range to get rid of that. So domain. Your x values can go as far left as negative infinity. So negative infinity. All the way to how far does your x values travel to the right? All the way to positive infinity. And you can use this notation, or you can use interval notation, which will mean negative infinity, comma, infinity. Right? This is notation with inequalities. This is notation in interval notation. And then my range. What's the range of this function? All right, well, how low does this graph go? Well, it almost gets to 0, but never touches 0. So your y values are greater than 0, never touching 0. And how high does this graph go? Well, it's going to shoot up to infinity, so all the way up to positive infinity. And again, the other notation is 0 is less than infinity, both with parentheses. All right, so in a nutshell, these are your exponential functions, and again, we'll do more and more and more and go from there. Okay, see you guys soon.